Hello everyone, this is Dr. Hopkins with your next video. Here we're continuing our discussion about equilibrium and using equilibrium constants. So the first thing we're going to discuss is the idea of an equilibrium with a different phase of matter. So if we're not all aqueous, like this example we had before, where we have our silver and ammonia, we can write our equilibrium constant as such, which we did in the last video. So what if, and in that case we used concentrations of molarity, everything was divided by the standard state. So as a review, so what if these reactants and products are actually gases? Okay, so here we have an example with N2O4 coming apart into two NO2s. Those are gases. We can't write gas concentrations as molarity, so how do we express that? So we're going to use an equilibrium constant with a subscript P for pressure. And so we have our equilibrium here shown again. And so instead of using molarity, we're going to use partial pressures. Now a partial pressure, if you didn't know, so we're looking at a mixture of NO2 and N2O4. The partial pressure of NO2 is equal to the mole fraction times the total pressure. So the mole fraction of NO2. The mole fraction is just moles of NO2 divided by the total moles. In this case, it would be the total moles of NO2 plus N2O4. And the P total, or the total pressure, that's something you can actually measure. That's a measurable quantity. Okay, so then we would write our equilibrium constant. Now, once again, it's not any different. It's still products over reactants to the exponent of the stoichiometric coefficient. So we have the partial pressure of NO2 squared over the partial pressure of N2O4. If we were then to substitute in our partial pressures and our mole fractions, we could do this. And so we would have, we would square our mole fraction of NO2. We'd have just the N2O4 mole fraction, and then P squared over P, which would sum to, so we could pull the pressure out. So we divide one of the pressures out. We pull that pressure, the total pressure out, and then our equilibrium constant is just the ratio of our mole fractions of the components. Now notice, once again, we have to have our equilibrium constant be unitless, so we're dividing by a standard state. In this case, a standard state is 1 atmosphere or 1 bar or 760 tool, whatever it is, in order to make this unitless. So what happens if we have something that has multiple phases? So for example, here we have lead chloride solid, we put it in water, it dissolves or dissociates into lead 2+ and 2 chloride ions. Those are aqueous. The lead chloride is solid. It's called a heterogeneous equilibrium. And remember, in every case, we're dividing by a standard state. So if we have a concentration, the standard state is 1 molar. If we have partial pressure, the standard state is 1 atmosphere. So what is the standard state of a pure liquid or solid? It is actually the pure liquid or solid itself, which means that we never actually include them. They divide out to 1 every time. They always add a unity to the equilibrium constant. And so that means if we were to write the equilibrium constant for this reaction, we would just write, in this case, products. We have no reactants that would factor into our equilibrium constant, and our chloride is squared. Same thing if we had a pure liquid. So here's an example where we have acetic acid dissolved and water. It reacts with water to form H3O plus acetate ion, so CH3CO2-. This is something we're going to do quite a bit in the near future. But notice we have 3 aqueous components. Those are going to be molarities. Those are going to factor into the equilibrium constant, but the water is not. And so we will write the equilibrium constant for this reaction. It would just be the concentration of H3O+ times the concentration of the acetate divided by the concentration of the acetic acid. Water divides by the liquid, and it just turns into 1. So basically, we can't affect the equilibrium by adding additional solid or taking solid away, or adding additional liquid or taking the pure liquid away. All right, so now we've established how we can write the equilibrium constant for concentration or reactions that are all in aqueous solution, where we have concentrations. where we have heterogeneous equilibria, where we have reactions in the gas phase. Now let's see, what can we do with that K? Now that we can calculate an expression for it, we know how to do delta G and calculate K from our free energies. What do we do with this K? Other than just calculate it and hey, wonderful, we can do all this. We can determine final concentrations of a reaction at equilibrium, which is actually quite useful. If you were to run a reaction, you say, well, what's going to happen? What am I going to end up with? It'd be nice to know ahead of time, hey, this equilibrium says I can only get this number of molarity of this component at the end. So let's start with an example reaction, and we're going to start with an acid-base reaction. So like I said, we're going to do a lot of these. So we'll have HClO, so this is the acid's going to react with water. We're going to generate H3O plus and ClO minus. So we had a similar on the last slide where we had acetic acid. So we have the K, we can look up the K for this, or if we were to do all of the delta G's of these formations, we could figure out the delta G of reaction, use minus RT natural log of K, and determine this. So when it turned out, it's 2.9 times 10 to the minus 8. So if we were to write this equilibrium constant, we now know we could ignore the water, we put products over reactants. And so let's do a quick calculation. If we started with 0.1 molar of HClO. We've set this problem up. Let's go through and solve this problem. So we have 0.1 molar HClO. We want to know the concentrations. It's an S. Oh, we need an S. We have our reaction. So we have our HClO. We have H2O, H3O plus, and ClO minus. What we're going to do is set up an ICE table. Okay, so ICE is initial change in equilibrium. The equilibrium concentration is what we're going to use in our equilibrium constant to determine the final concentration. So we're going to set up a large algebra problem. All right, so let's start with the initial. Before we allow it to come equilibrium, we have 0.1 molar, so we're going to say 0.1 molar in there, and I'm not going to put the molar, it's implied. Water, what's its concentration? I don't care because water doesn't factor into the equilibrium constant. So we're going to get rid of it. It doesn't matter what its initial change or equilibrium is. Our H3O plus, are we starting with any of that? We're going to say no. ClO minus, no. That's all going to come from our reaction. So our products are all going to come from a reaction. So then what do we represent change for? Like I said, this is an algebra problem. Algebra usually means we have to have variables such as x. So let's say as this reacts, we're going to lose HClO. So we're going to have minus x, and I'm going to make it 1x because there's a stoichiometric coefficient of 1. And so then also, if we go over to the H2, remember we're ignoring H2O, we go over to the H3O plus, and then we look at its stoichiometric coefficient. For every 1 HClO we react, we will get 1 H3O plus. Since it's minus x, we're going to make this plus x. Okay? And then for ClO minus, once again, the stoichiometric coefficient is 1, so we also put a plus x. So then we just add these two columns together to get the equilibrium concentration. So 0.100 minus x, we don't care about water, sorry, it's in there. 0 plus x is x, 0 plus x is x. So those are our equilibrium concentrations. Now, if we were to write the equilibrium constant expression, remember it's products at equilibrium over reactants. Now, they're all 1-to-1, so there's no coefficients here. HClO, okay, so it's H3O plus over ClO minus. And then if I have room, times 10 to the minus 8, remember from the previous slide. And so that means our K will substitute in for H3O plus is 8x times x over 0.1 minus x equals 2.9 times 10 to the minus 8. And that's equal to x squared over 0.1 minus x equals 2.9 times 10 to the minus 8. Okay, now what we have is a quadratic. And we just need to solve that. And we go back to our PowerPoint. So we've written this out. You'll notice we have our K, we have the equilibrium constant. Now I've written out the actual quadratic equation. So if you wanted to go solve it yourself, you can use the solver on your calculator, you can solve, you can plot it, and so forth. But if you do that, you'll find that x is 5.38 times 10 to the minus 5. So that means our concentrations of H3O plus and ClO minus are 5.38 times 10 to the minus 5. The HClO is 0.1 minus that number. Well, you'll notice 10 to the minus 5 is pretty small. So basically, the concentration of HClO doesn't change. It's just still 0.1. So it's unchanged from the initial to equilibrium. So that's going to lead us to an assumption we could potentially make later on. But at this point, we have our concentrations. That's what we can get out of these equilibrium constants. So the takeaways from this: pure solids and liquids don't factor into the equilibrium constant. You can add them all day or subtract them all day. It's not going to affect the equilibrium. Depending on what your reactants are, it changes the units they are, but they end up in K. We always divide by a standard state so that K is unitless. We've demonstrated how useful K can be so that we know what our final concentrations will be at the end when thermodynamics is done with it. The equilibrium concentrations will be represented by that. And we've learned how to use ice tables, and we know that algebra is fun. So until next time.